to the webinar sponsored by Fuji Techno, ladies and gentlemen. We're delighted to have Dr. Charlotte Wiles as our keynote speaker. Dr. Wiles is key opinion leader in the flow chemistry field. SelectBIO has been running conferences in the flow chemistry field for about 10 years in the UK, in the US, as well as more recently in Japan. And Dr. Wiles always gives fantastic presentations, and we're honored to welcome Dr. Wiles today as our opening speaker. Ladies and gentlemen, if you have questions, please kindly type them into the Q&A box or the chat box, which is at the bottom of your Zoom screen, and we'll take the questions in the order received. Also, what we'll do is, upon the completion of the webinar presentations, we'll go through and ask you to raise your hand so you can ask your questions in real time. So we'll try to make this as interactive as possible. So without any further ado, ladies and gentlemen, we'd like to welcome Dr. Charlotte Wiles as our opening keynote speaker, and Dr. Wiles will be now delivering her presentation. So welcome, Dr. Wiles. Thank you.
Thank you very much for the kind introduction and the opportunity to talk with you all today. So good afternoon, everybody. As you've just heard, my name is Charlotte. I'm the CEO of Chemtrix, and we're a flow chemistry company that focuses on the reactor itself. But here today with also Mr. Morikawa from Fuji Techno, we're going to give you an idea of all the other ancillary equipment that is actually needed to successfully run a continuous flow setup. So we're going to look at that going from R&D, when you might just have the idea of running flow chemistry instead of batch, all the way through to how people have implemented at an industrial scale. And we'll try and give you a breadth of examples from pharmaceutical through to specialty and fine chemistry. So what you can see traditionally is that we have typically problems when we scale chemistry in batch vessels. When you go from maybe a 25 ml round bottom flask up to 100 and then a litre, you tend to see a loss of selectivity, reduction in yield, failure of reactions, difficulties controlling the process. This could be exothermic, it could be gas evolution. So as we're changing those surface to volume ratios of reactors, you start to see variations in the chemistry that you're developing. And what we're looking at with continuous flow is minimizing those changes by minimizing the scaling influence. So we maintain a high surface to volume ratio, we maintain thermal control and mixing efficiency. So the goal behind continuous is not to put batch processes in flow, but it's to look at those processes that are difficult to control and have disadvantages when you increase the scale of manufacture. So we're looking at intensifying a process. So that may be running solvent-free, running at higher temperatures. And as a result, having a smaller footprint installation. Part of this is also process control. So we put in a lot of digitalization, and this allows you to use advanced process control and machine learning. And what you can see here in the image, which is from AN Technology, a partner company that we work with, you have a traditional batch vessel alongside an actively mixed small footprint rotating tube reactor. So we're looking at using space more wisely in order to control chemical processes more efficiently. And since we're operating a reactor 24/7, the idea is that you leave the tap running, as Dave Agar of DSM used to say. So the amount of material you produce is directly linked to the size of the reactor that you use and the total flow rate that's going through it. So you leave it running for a day, a week, a month, a year, depending on how much material you'd like to generate. So the basics of a flow reactor are the reactor itself, obviously, the dosing system, the method of temperature control, and the means of collection. So for those of you that have not used flow before, it's a really straightforward concept. You separate your reagents, into vessels, you pump them into a device where they meet and mix. You thermally regulate that device to the required temperature to either put in the amount of energy to start the chemistry, to withdraw the amount of energy that's released in an exotherm, or to stabilize the process conditions. And then the material is constantly evolving from the device. So you're collecting and you work on the downstream processing specific to the particular chemistry that you're performing. And the difference here compared to batch is that you start to understand the requirements of your chemistry much more closely. How long does the material need to spend in the device? What precise temperature do you need to employ in that device to get the maximum conversion and the maximum selectivity? So we're often designing the reactor for the process rather than changing the process to suit the batch vessel, either by dilution or slow reagent addition or reduced temperature operation. So you can see this is quite a significant change compared to your batch practices. So whilst we are a reactor company, we do see that the pumping and the dosing into your reactor is the most critical element. If you've got a varying reagent stream, your stoichiometry between A and B can be varying, and therefore your product quality will be different. So from a static reactor perspective like ours, we need a very precise, constant stream of reagents and a balance between the stoichiometry in order to be really sure we're going to get a very good quality product. So here you can see a couple of examples of how the technology is developing. People are looking into small skid-based pumps, portable devices, so that you're able to choose a high-quality dosing system to go alongside your reactor. You can see on the right here, a supermetering pump at the lab scale from Fuji Techno, and the following presentation today from Mr. Morikawa will give you insight into how this pump works and how it delivers the smooth flow profile that's needed for a continuously operating flow reactor. The reactor itself, you can see an example of here. We have a plate reactor. This is one of our Plantrix silicon carbide production scale devices. You can see it stays relatively small. So this is 0.8 meters in height to give you an idea of the scale in the image. And you can see we're temperature controlling by connecting to a recirculating thermostat, in this case, a Huber. And what this does is it gives us very tight temperature control over the reactor module itself. And by expanding the number of modules in that reactor, we can change either the throughput of the device or the reaction time. So into such a device, we would be pumping from the pumps you've just seen, and we thermally regulate with a recirculating chiller or heater. We also need to know what's happening inside the flow reactor. So unlike batch, where you may take a sample, take it away for quality assessment, here we often use a lot of in-process monitoring. That could be flow, temperature, pressure at the simplest level, or it could be with inline analytics such as infrared, as you see here on the left, or even inline UPLC using a system like the Waters Patrol unit you can see on the left. You have to match your PAT to the reaction times that you can anticipate that are going on in your reactor so that you can mitigate any changes and perform corrective action. If you've got a 10-second flow reaction, there's no point having a 10 or 15 minutes offline HPLC method to qualify what's going on. So you have to match the technologies for the particular process that you're looking at. And then if you're considering downstream, are you going to collect the material in a batch and process it using traditional methodology? Or are you going to use inline techniques such as phase separation, liquid-liquid extraction? And you can see an example here of the Zyput liquid-liquid separator, ranging in size from a really small 10 mil per minute lab scale unit up to about 3 litres a minute for production. So you start to look, this is an expansion, not just of the reaction step, but also of the upstream and downstream activities in producing your particular chemical. You then need to combine all of these parts, and we see a trend in this being modular and skid-based, where people are looking at having small compact units that either, in this case, as you can see, go into a pilot fume cupboard, or it can fit and be positioned within a factory in between existing infrastructure in the space between your vessels, for example. So in this example by Fluid in the Netherlands, what you can see here is we have on the right hand side the feed vessel skid, and then in the center you have the flow reactors in orange, got a little thermostat here, temperature controlling, and then receiving on the right hand side. So the workflow is going, as you see from the schematic, dosing, reaction, collection. So for those of you that are new to flow, you might be questioning when to actually start doing flow chemistry. What are the conditions that you should be looking for? Now, for us, a significant aspect of where flow chemistry has benefit, particularly at a production scale, relates to the performance of the reaction in a small channel device. So we're looking at performance connected to scale of operation. So if you have a high surface to volume ratio, you're typically looking at fast reactions, maybe energetic with unstable intermediates, or even hazardous raw materials or intermediates that you're producing. You can be looking for high or low volume production, depending on the reactor size and the time you're operating for. And essentially, we're looking at intensifying a process to expand capabilities beyond those that are usually accessible with batch. You don't always get all of these conditions met with flow. It's process specific, and you need to look at what aspect you're trying to address. Maybe you're looking for a new route, maybe you're looking to accelerate supply chain security, or maybe you have, as I'll show you later, high potency compounds that you want to contain and minimize operator interference with. So we're typically addressing energy costs, waste generation, and process efficiency and process safety. So if you keep that in mind through the examples that we show, you can start to correlate this to your own chemistry and look for opportunities as to where you can employ the technology yourselves. So in order to go with flow from lab to manufacturing, there's really, for us, a series of steps that you need to take. You need to really theoretically understand what it is you're trying to do and why you're trying to convert or implement the flow process. So together with your team, R&D, all the way through to manufacturing, we think it's really important to define your process targets and clearly identify what the problem statement is that you're trying to solve. This can give you then theoretical opportunities for improving the process, and that helps you to define what the equipment could look like and how you could implement it. If this then looks positive, you work on a basic feasibility study, and this would involve typically lab trials in order to deliver that first proof of concept against your problem statement. And then the next step is to outline the milestones for optimizing that process in order to get it to a process that's suitable for the small or large scale manufacturing. Once you've got those parameters in mind, that's when you need to be looking at the evaluation of the hardware. What kind of pump specifications do you need? What thermal regulation are you requiring? What type of reactor? And this gives you the detailed information for your engineering design. After that, you go into your realization phase, which is going to be designing the plant, pilot, or production, commissioning after you've built and tested, of course. So what you can see is we go really from a chemistry domain through to a process operator domain. So there's many different skill sets along this track where you need to have a mix of chemists, chemical engineers, mechanical engineers in order to make this transition successful. So once you've got your idea in mind, you need to do your basic proof of concept and your design work. And we typically do this at the milligram level using devices such as the glass one you can see in the bottom right-hand corner. We're looking at using small devices because it gives us really short reaction times without using a large amount of raw material. And it allows you to change parameters quickly because you don't have a large hold-up volume in your device. So we would typically be screening reaction ratios of flows, reaction temperature, and time in order to understand the operating window for the particular chemistry. So here you can see a straightforward transformation from an alkyl bromide into a organic azide using sodium azide as the substrate. Here you can see we've got a reactor IR flow cell positioned after the flow reactor. And what this allows us to do is to, in real time, monitor the consumption of the sodium azide and the evolution of the organic azide. So this allows us, with design of experiment, to control the process and also understand the key parameters that affect the optimization of this particular chemical transformation. If you also use offline techniques, here we've used GC, FID, and what we're looking at is the influence of temperature on the conversion of the bromide through to the organic azide. And from a safety perspective, you would see we're typically working below 50 degrees for the organic azide production. This takes a long operating time, 12 to 18 hours typically. And in flow, we see almost no reaction under these conditions. So by steadily increasing the temperature, what you can see here is the conversion increases. And then at 175 degrees, we've got complete consumption of the bromide and conversion into the organic azide. And this then allows us to see if we can change the raw material from a mesylate to a bromide to a chloride. Can we actually decrease material costs? So without stepping out of the lab, we're already able to look at parameters that influence productivity, manufacturability, and cost of production. So you get a really early indication of viability of manufacturing. We looked at a lot of chemistries in the pharma space, as you can imagine, where people are looking for low quantity, high quality material production. So here, together with our partner Alphora Eurofins, you can see a piece of work that they've patented on the molecule picato, which is a multi-step chemical process that consists of a series of protections. Here you can see a deprotonation followed by an acetylation. And then here we've got a pH adjustment at the end in order to access ingenol butane, the key intermediate in picato. There was a desire to reduce the number of operating steps by stripping out the protecting group chemistry, and that was something that needed precise control, and we investigated together using a flow reactor. So here you can see the layout of the flow reactor. We take the ingenol precursor, you're adding together with the base, which you can't see here. We add in the acetic anhydride derivative, and then in the flow channel, you're actually performing the acetylation in the 3 position that you can see here. And we implement an aqueous acidic quench in order to terminate the reaction precisely and stabilize the reaction product. And what the partner was able to do here was employ no protecting group and minimize the acetylation on the other hydroxyl functional groups. So there's a patent out on this process that will give you more information if you're interested to learn more about this specific case. A nice aspect of a static flow reactor is that it's a sealed tube or pipe, and this means that you have no headspace within the device. So unlike a batch vessel that will always be partially filled and have a headspace that needs to be swept and controlled, in a flow reactor, we can have a completely filled reaction volume. This can be really handy if you're working with unstable intermediates that can interact with oxygen, for example. And here we've got a case where we're looking at a ring opening polymerization that was traditionally done at the milligram scale and had to be done within a glove box because of the moisture sensitivity of the reaction. And what you can see here is by controlling the reaction time and the amount of organocatalyst that was used, we're able to use outside of the glass box in a standard fume cupboard. We're able to perform these ring opening polymerizations. And we were able for the first time to look at the temperature and time influence on these chemistries really easily with a Peltier controlled flow reactor. So what the authors were able to show was a reaction time as low as 2 seconds was possible to perform these functionalized ring opening polymerizations, and able to get a really low polydispersity on the material produced. Because the reactor can be run continuously, you can influence the amount of material you produce. So they were able to obtain gram scale quantities of these materials for the first time, simply by dosing material from the syringes through the flow reactor and continually collecting it. Telescoping for me is one of the really interesting aspects of continuous flow. You can give each reaction step the precise conditions that it requires. So if you want to perform a hot reaction step followed by a cold, you don't have that lag time that you have in batch, where you would need to warm up a vessel, give it the reaction time, cool it down before you can perform the next step. You can actually hold your devices in 2 different thermally regulated conditions. And as the material flows through one reactor to the other, it experiences the different temperature profiles. And this can be really useful where you have very different requirements from steps, such as an endothermic versus an exothermic reaction step. And in the case you can see here, we were targeting a API, lomustine, and it was developed by the researchers at Purdue University and is now going to be outsourced into production with an SME. And they focused on an alkylation step followed by a key nitrization step to form lomustine. And they were actually combining the technology development with desorption, electrospray, mass spectrometry online, so that they could really quickly identify viable reagent and solvent combinations for the cost-effective selective production. And what they're able to do with these microscale reactors is isolate the material at about a dose an hour, and then with a small footprint production scale reactor, you're able to meet the annual demands of this raw material. If we go slightly larger in scale, you can see here in the background, we've got our Protrix silicon carbide flow reactor connected up to the new React IR from Metal Toledo. We're able to increase the amount of material that you can produce from a fume cupboard, really quite straightforward. So here from a reactor running at a few tens of mils per minute, we're able to perform oxidation chemistry that would typically be quite challenging using the direct oxidation principle from hydrogen peroxide, as you can see here. And what we're doing in the Dakin oxidation is taking an aldehyde and oxidizing it through to a catechol. So this was a piece of work we did with a partner who had stopped doing direct oxidations after a safety risk on the factory from storing large quantities of hydrogen peroxide. And they started to use a multi-stage chemistry in order to access catechols. But they could see by having a small footprint contained reactor, they could go back to a direct oxidation, giving them a shorter synthetic route, reduced reagent usage, and an increased production rate of this key intermediate for them. So key to the use of peroxide was a metal-free reactor to minimize any decomposition and runaway risk, and something with integrated thermal control so that you could really tightly temperature control that exothermic transformation. And here we're using about a 30-second reaction time compared to a fed batch time of 6 hours. And that was able to give us just under 5 kilos of material in an 8-hour period. The nice thing here was we were using aqueous sodium hydroxide as a solvent. So actually the product was biphasic, liquid phase catechol, and then the waste stream was separated using a Zyput liquid-liquid separator to give you your aqueous waste easily separated in line So again, a lot of the work we do is about control or accessing temperature conditions or parameters that are not typically accessible in a batch vessel. And that's particularly the case here with this piece of work we did together with Oliver Cappe's group in Graz and AstraZeneca over in the UK. They were looking at the preparation of this reduced material here in red as an intermediate in an API. So this is a phase 1 clinical trial material. And you can see here, key transformation was a Wolff-Kishner reduction. So ketone, hydrazone, elimination. And typically the Wolff-Kishner reactions are performed at high temperature. They need high pressure, long reaction times, typically quite slow with low yield. So in order to address safety concerns associated with doing this type of chemistry, we looked at first performing the hydrazone inflow, minimizing the exposure to hydrazine and hot hydrazine at scale, and then looked at the elimination in the presence of potassium hydroxide at a moderate temperature. Now, if you combine the use of hydrazine and these highly caustic environments, you would again need to be stepping away from a metal reactor, and we used the Protrix silicon carbide reactor for the process development. What we were able to do together with the researchers at Graz University was to demonstrate that by controlling the reactor and removing the headspace, we could decrease the amount of hydrazine because you're not getting losses into the headspace, and we could reduce the reaction time down to 20 minutes with an increase of 40% in the actual yield of the product. So this was a nice example of being able to use process intensification for yield improvement and selectivity. A really recent example that you can read about in this month's edition of OPRD is a chlorination that Professor Fenner Chen has developed as part of a route to vitamin B1. You can see the chlorination in our reactor is only one stage of the process. There's also downstream additional processing. So we often find that the flow reactor is only one element of a multi-step process and a series of unit operations, but it's always looking at focusing on steps that need to have increased control, reduced waste generation, or looking at improving selectivity to minimize isolation costs. And in this case, this was targeting the 3-acetyl 3-chloride dihydrofuranone, which you can see here on the right. And we're looking at the monochlorination. And what they were able to do with a 30-second reaction time at room temperature was access this intermediate in a high yield and purity, and then look at the decarboxylative acylation downstream as a key precursor to this vitamin B1. Small scale manufacturing is a really big trend that we see within continuous manufacturing, especially looking at the distributed manufacturing. Can you start to step away from world plants and global manufacture, especially of APIs? And can you actually start to produce in the country that needs the material itself? And this results in much smaller footprint infrastructure and potentially putting infrastructure into countries that typically don't have API manufacturing capabilities. And this is an example of that by Professor Paul Watts at the Nelson Mandela University in South Africa. He's specifically targeting bringing back manufacturing, or in some cases, establishing manufacturing. And particularly in South Africa, where the vast majority of APIs are actually shipped into the country from other manufacturing countries and only formulated locally. He sees that this is an opportunity to take control over the API pipeline, manufacture the API and formulate it for the local population. So there's two areas that he focuses on, HIV medication, antiretrovirals, and more recently, diabetes drugs. So this is work that also came out in the last couple of weeks in the European Journal of Organic Chemistry. And it's looking into the production of a series of diabetes drugs, specifically for type 2. And here you can see it's a multi-stage process where you first form a reactive intermediate and then couple to form the target product. And by switching out the R group here, you can produce two different diabetes APIs. So here you can see Faith producing the work. We've got the glass-based multi-stage reactor here. And what they're able to demonstrate, as I say, is by switching out the R group, they're able to access 4 different anti-diabetic APIs. And here, from a reactor the size of 15 by 15 centimeters, they're able to access anything from 0.5 kilo up to 4.5 kilos of that API from a laboratory fume cupboard. So this now starts to give you an idea that you're up at the typically 30 kilos a week productivity from a unit that's sitting within a laboratory fume cupboard space. So this really gives you visualization on how compact these systems can be and how you really can step towards local manufacture and small volume production without having to put up large infrastructure chemical plants. And again, footprint was a reason for this particular case with Buchem in the Netherlands. They're a contract research organization and manufacturer, and they were looking to be able to produce about 800 kilos of an intermediate for a customer. And they found that when they were actually doing the chemistry scale up, anything over a litre, the chemistry started to fail as they lost control over the headspace in the reactor. As a result, we looked again at a headspace-free flow reactor as a mechanism of continuously delivering this intermediate that they were trying to produce. So this actually was a cooperation between the end user, ourselves as process chemistry developers, and Flowid as system integrators to build the automated platform that you see on the right. So the steps we took were, we did the process development. We then went to Flowid with the basic design information. They did the system integration. The unit was delivered to the customer, and Buchem then produced the raw material under the recipe that we developed for their customer. And the interesting thing here was, in the same footprint they could make a kilo, they could then make the 800 kilo market requirement and produce more material than was needed, and therefore serve additional customers. So it has reduced inventory, you're constantly manufacturing, you're not needing to stockpile, and you have improved process control for something that was a lacrimator and typically difficult to manufacture at scale. This is an example together with PI, process intensification experts in India. And you can see also Fuji Techno here, we're a partner on this chemistry development. And this is a piece of work done with CIPLA to look at compact API production. So it's a multi-product, multi-step production plant that was retrofitted into an existing asset base within their production environment. And the idea is that you have process flexibility and safety, speed and security of scale up, and you again reduce the inventory of any hazardous reagents, giving you stable product purification. And what you can see here is just our flow reactor, but also outside of the shot are the supermetering pumps that you'll hear about next. And we also worked with AM Technology, an actively mixed flow reactor company, for the next reaction step and a reactive extraction. So this was a very compact setup, and process intensification experts, PI in India, can give you more information on how this project ran and the type of work that we're able to do together. So small footprint, compact, intensive processes, as I say, is the reason that people are going towards continuous flow. Specifically in the contract manufacturing space, we see companies needing to expand their footprint, expand the amount of products that they can generate for companies, but they're often restricted by batch capacity. And an example of this is Anthem Biosciences in Bangalore in India, who were rapidly expanding from 2007 to 2015, simply by increasing the acreage of their plant. And at a certain point, you come to the boundaries of your plant and you have to look at how more smartly can you actually use the asset base and the area that you have. So in 2017, working again with PI, they set up a flow lab and really quickly progressed from process development for customers through to manufacturing, with half a metric ton in 2020 realized. So what's at the heart of the scale up are two Plantrix flow reactors that give them flexibility to a lot of different corrosive chemistries and modular access to different size reaction paths. And this now allows them to operate at kilos to metric ton per month. An additional benefit they found was also reduced effluent generation. So downstream improvements can also come about by improving your chemistry. If you go towards a more dedicated solution, you can see here an integrated skid. This is a piece of work we did with Fluid again for the customer MSD. And this is a production skid that's not designed to be flexible. It's for one specific process. And you can see a few cubic meters gets you a highly productive continuous flow plant. And this unit was designed to sit between batch steps within a traditional batch plant so that you could do the upstream in batch, perform the flow reaction, and also telescope it onto downstream. It is a second generation process, so the process development was all geared at reducing reaction steps, increasing yield, and reducing cost of goods. And this had the positive benefit of a significant drop in the process mass intensity of the process as well. So we see where APIs are concerned that there's a lot of second generation development, but also now those early phase one material deliveries are also being performed using continuous flow. So one of my favorite aspects of flow is that everything is contained within the device. So it's incredibly safe to operate. And this is shown here in a case with Ajinomoto Biopharma Services, who had a high potency product that was energetic, 3 exothermic steps, all requiring really slow reagent addition in batch. So we saw together at the end of 2017 that this was an opportunity for continuous flow to increase the safety associated with the exotherms, but also to contain multiple operations and minimize operator exposure. And by doing this, we're able to increase the productivity for this particular process a factor of 2 compared to batch. And this also then opened up batch capacity that could then be used for other chemical transformations, since they're a CDMO. So at this stage, 70% of the process was converted into flow. And they used a series of small mobile modules for pumping, reaction, and downstream operations that they were able to test within the laboratory and then combine and put into the production environment. They also got a lot more process robustness via automation and developed this work internally themselves. And then last year, during COVID, they actually increased the productivity further with a larger scale unit operation. Here you can see in the center a Plantrix 5x5, and on the left you've got the dosing pumps and the downstream steps. So this remains 2 continuous steps, 1 batch step, and at the point of writing this last month, they generated just over 500 metric tons of this active high potency OEB5 compound. So in addition to the pilot scale advantages, they were also able to reach the target price set by the customer by using continuous, and they were able to increase the annual output up to 250 metric tons per year was the limit on the dedicated batch synthesis unit. So again, you can see they've over doubled that. And it released 2 6,000 litre vessels that can be used again for additional batch processes. So the outlook for this particular process is to further improve that batch step downstream, and this will allow them to release more capacity in the flow reactor. And ongoing development work has shown that that third step can also go into flow. So a plan is now a second installation to increase capacity even further for their customer, and this will be on a second site with all 3 steps continuous. So this is a really nice story of how somebody's gone from the lab all the way through to manufacturing, and is now looking at ramping up manufacturing as that molecule lives on and the market demand increases. So it's, as I say, it's not all about APIs. There's a lot of specialty chemistry done continuously as well. This is a selective aromatic nitration, where we're looking at using a mixed acid. So in this case, sulfuric acid to dissolve the starter material, and then precise dosing of the nitric acid in order to give mononitration. Here, you would typically be using a solvent in batch to dilute so you can control the exotherm, but that wasn't needed. The reactor is able to cope with that heat release by having that recirculating thermal fluid. And what we're able to do here is meet the target specification and increase production rate. So going from a pilot reactor that you can see here, about 5 litres per hour, to multiple reactors just under 700 litres per hour. So what we look at doing is maxing out the productivity of a single unit without losing performance, and where production requirements need more, you then put material in parallel in order to generate more. This gives you flexibility, of course, in increasing and decreasing production rate that actually can match your market demands. And I think in the second to last example here, what you can see is safety features that we're targeting. A specialty chemical product, which is a dye, reactive intermediate, and a very high specification still on the colour. And what you can see here is we are combining sodium nitrite to make a diazonium intermediate that then gives rise to the dye that people are looking for clothing and specialty applications such as cosmetic applications in contact lenses. So you need a lot of thermal control here because the diazonium salts are highly unstable. People don't like to hold them on large volume because of their runaway risk and decomposition. So here we're able to deliver just over 500 litres per hour of these materials with a simple hold volume of about 220 mil. So that's no bigger than you'd be running in your lab fume cupboard, but accessing very high production rates. So here you can see an example of how people put the reactors in parallel. This was a piece of work with DSM, Patheon now, Thermo Fisher Group. And what you can see is you've got multiple reactors operating in parallel, piping in the raw materials from the floor above, and the black pipes show you the thermal regulation coming from a central supply within the plant. And this is essentially a service shaft within an existing plant, so it's taking up a really low footprint. And we were targeting here a selective mononitration of a diol as a precursor to naproxen. So corrosion resistance was incredibly important. So that was our brace-free silicon carbide modules we used for the reactor. And the goal was to reduce the amount of solvent that was typically used as a heat sink for this large-scale API production. And what you can see in the graph here is stepping from pilot batch into pilot continuous, there was a dramatic reduction in the amount of organic solvent required in order to control the process. And this was further improved stepping into production so that you're able to generate a lot less waste whilst stably performing this selective nitration. So industrial scale continuous manufacturing, it's not new. It's used in oil and gas, it's used in the food industries, but it has over past years started to come in as a new technique for fine specialty and agrochemical applications. And we're traditionally targeting these lower volume, higher value products, with advantages being smaller footprint, increased product quality and safety. But from a business perspective, just-in-time manufacturing, reduced capex and shorter, low-risk supply chain. So we see that as an answer to part of the challenges that we've seen for COVID, that this could be the catalyst for change, where people are looking at local, just-in-time manufacturing and starting to produce in multiple locations the same material. So it's a very big difference to how stockpiling used to happen in the past, but we are seeing this now, especially in the API and fine chemical space, to really become active. So with that, I'd just like to leave you some images of small agile production units. And after Mr. Morikawa's presentation, we'll be happy to take any questions. So thank you in advance for your questions, and we look forward to discussing further with you.
Thank you very much, Dr. Wiles, for an excellent presentation. Ladies and gentlemen, as Dr. Wiles mentioned, we'll take questions and do the Q&A after Mr. Morikawa's presentation. So once again, please join me in thanking Dr. Wiles for a very engaging presentation as always. And we'll now look forward to Mr. Morikawa. So Mr. Morikawa, if you would kindly unmute, turn on your video and share slides, we're ready to go. Thank you very much. Thank you, Dr. Wiles. Thank you. Hello, Mr. Morikawa. We can hear you, but we can't see you. And
okay, I'm just making adjustment now.
Great, thank you very much.
Okay. Hold on. 비디오開始じゃないの?
共有ですね.
See. Okay. Jeff, I have some difficulty to find the video, so I just want to start my presentation. Is that okay?
Yes, that's fine. Thank you very much. Please proceed. Thank you very much.
Thank you. Okay, good morning or good afternoon, ladies and gentlemen. This is Harry Morikawa of Fuji Techno. Welcome to my presentation on non-parasitic metering pumps. The aim of my presentation is to highlight the benefit of our metering pumps, differences to look out for, and pumps suitability in the continuous flow applications. To maximize productivity and product quality, it is essential to have a non-parasitic flow of the liquid with high accuracy and stability. Only non-parasitic flow enables you to achieve perfect mixing ratio of various chemicals. Metering pumps are often the preferred choice of continuous flow applications. They are classified as reciprocating types, such as a piston, plunger, and diaphragm, or rotary type. A typical example is a gear pump. Their primary function is to accurately feed predetermined volume of a liquid into a process or system. In reality, hold on, I'm sorry, I jumped to the next page. In reality, pumping accuracy are different from one type to another. Sorry. So Selecting pump for the application, user must pay attention to properties such as metering accuracy and stability, as well as a level of pulsation. In comparison to the gear pumps, reciprocating type metering pumps are less susceptible to the physical parameters of the liquid. However, without improvements in the basic design, reciprocating type metering pumps generate large pulsation in the suction and the discharge process. The sine wave shown reflects the flow velocity during the suction and discharge cycles. To minimize pulsation and improve discharge accuracy, metering pump manufacturers have come up with various design. I'd like to show you two very good design. The first one is jumping the page and page. First one is a crank type triplet plunger. The discharge accuracy is typically greater than plus minus 5%. Discharge accuracy is a deviation in the flow rate. In theory, pulsation in the magnitude of 14.2% is generated. Accumulator is absolutely needed for the reducing the pulsation. Here, it is worth noting that the properties of accumulated liquid can change over time. This graph shows typical output of a pump with a double plunger. This design is often used for the diaphragm pumps. Discharge accuracy is typically higher than plus minus 1%. You can see the discharge curve is different from the suction curve. Compared with the discharge process, suction process is shorter. This means the suction speed is faster than the discharge speed. So differences in the speed causes pulsation. So although it seems that there is no pulsation in the discharge side, pulsation does actually occur. Animation shows operating principle of our supermetering pump. Motor attached to the pump rotates pump shaft, and three cams move with the shaft rotation. This rotation provides reciprocated movement of plunger. So the plunger push up and pull down the check balls in the pump head to close and open valves. There are three suction valves at the bottom and three discharge valves in the upper section of the pump head. Interconnecting channels links those valves. So each plunger moving with the same manner with 120-degree offset. The first plunger start is just a discharge stroke at 0 degree, a second at 120 degrees, and third at 240 degrees. Design of each plunger incorporates 6 phases of movements and at an increment of 60 degrees within one revolution of cams. This animation shows suction and discharge flows created by 3 plungers. So the combination of these movements ensures the flow rate remains steady at all the time, and width is one revolution of the cam. As you can see, 3 specially designed cams are driving the plungers to the continuous discharge liquid at a constant rate, flow rate is proportional to plunger velocity. The deviation is typically less than plus minus 0.1%. Like other reciprocating pumps, inlet is at bottom and outlet is in the upper. However, unlike other reciprocating pumps, pump head of a pump can be put upside down to feed liquid particles better by gravity. So in designing of Fuji Techno pumps, many methods and tools are used to optimize performance. These include computation analysis, in particular for the design of check valves to achieve high accuracy and minimize pulsation. For instance, to compare effectiveness of check valve designs, 3 models of valve seats are created. Model 1 has a flat valve seat. Model 2 has a valve seat with a 45-degree tip angle. Model 3 has a valve seat with a 30-degree tip angles. Analysis utilizing a computational fluid dynamic software to simulate liquid flow, we can observe following behavior. Model 1 enlarged views over the XY and YZ over inlet are shown here. Sorry, I jumped to model 2. When valve is closed, backflow takes place and the result is pulsation. Model 2, with a vortex inside the valve, and because of vortex, backflow is restricted. Model 3, like model 2, there is a vortex on the inside of the valve. However, backflow is observed because of the marginal gap between bore and the valve seat. In addition to the modifying the pump design for the high accuracy and the lower pulsations, our engineers have developed the AI software to finely adjust the motor speed for minimizing the pulsation. Trace plots shows the difference between before and after activating the software. A pressure sensor is placed in the distal side of the pump to measure and send pressure data to controller. Control system developed by Fuji Techno captured the pressure values. As you will see, the fluctuation of pressure has a certain pattern of highs and lows. The software learns the pattern and adjusts the motor speed to calibrate output and minimize pulsation. Here's the adjustment of the motor speed. So, as a result, fluctuation of pressure after calibration is very marginal, very small. Please note, the finely adjustment of the motor speed is variable with our pumps because pulsation generated by our pump is very marginal to begin with. Otherwise, fine adjustment of the motor speed is very sensitive to the motor. So Fuji Techno's supermethane pump provides extremely high accuracy. Once a pump speed is set, you will have the same flow rate at all the time. Highest accuracy we have recorded was deviation less than plus minus 0.01%. Okay, sorry, I cannot control this one well. The slide shows the constant flow volumes in spite of variation in the discharge pressure. This is a very important feature for the continuous flow application with microreactors because pressure inside of the microreactor fluctuates. So you see the virtually same flow rate lines in the various discharge pressure. Okay, here is the extract from a list of chemicals supermethane pumps are able to handle. These include organic solvent, hydrogen peroxide, catalyst, surface active agent and water reactive reagent. One of our customers is pumping organic lithium 2.6 mole liquefied gas and liquid with carbon catalyzer. Slowly, particle size like 100 micron weight percentage 15 can be fed. And one customer has provided us with this data in reaction data sheet and told us that supermethane pump was able to pump hydrogen peroxide continuously. And the supermethane pump could pump basic substance containing sodium hydroxide as well. Experiment with other pump to feed hydrogen peroxide failed because bubbles are being created due to pulsation and sticking in the pump head. Okay, another application was to pump organic lithium, which has a very important role in synthetic chemistry. As organic lithium has a very high and fast reaction, it is essential to use pumps like Fuji Techno's supermethane pump for precise control of flow rate and mixing. Also, because organic lithium is a water reactive reagent, strict separation of air from organic lithium is necessary. One customer used 5 supermethane pumps to produce organic compound using hydrogen and organic lithium exchange reaction. Initially, customer could conduct a trial with syringe pumps for only a few minutes of reaction. Then the plant was designed to do continuous operation by utilizing the gas-free supermethane pumps. Here is an overview of a piping and instrumentation in the plant. This experiment was conducted in a lab at the Kyoto University, Japan. Polystyrene living polymer, which was produced by initiated anionic polymerization, was effectively trapped with a definitive ethylene, resulting organo lithium species could be used as a macroinitiator for the anionic polymerization of acrylic methacrylate to obtain styrene acrylic methacrylate diblock copolymers at a temperature much higher than that with the conventional batch method. So there are 5 models of supermethane pumps for the scale up from R&D in lab to pilot plant and mass production. Flow rate from 0.1 milliliter per minute up to 200 liter per minute. Maximum discharge pressure and the maximum viscosity vary one type to another. Please keep it in mind, our standard pump can bear from -30 to 120 degrees Celsius, and we have a high temperature version which can bear up to 200 degrees Celsius. So I'd like to let you see some pictures showing the installation of our pumps. This is a mini plant of Evonik displayed in AHEMA 2018. Plant is for the production of API and the intermediate. The pump is located at the base of the plant. So this pump got a maximum flow rate 565 milliliter per minute, and the maximum discharge pressure is 23.5 megapascal. A pump has a jacket for the heating up to 130 degrees Celsius. This latex certified skid consists of reactors, pumps, motors, instruments, sensors, and others. Maximum flow rate of each pump is rather high. It's 6 liters per minute. The parts in contact with the liquid are GMP FDA certified. Our standard liquid and part material is SAS316. Optional materials are Hastelloy, titanium, PTFE, and PEEP. Okay, our supermethane pumps can use to pump some liquid with the particles, but however, due to the high demand for the pump to cope with the wide varieties of slurry with a high accuracy, Fuji Techno is now developing a unique diaphragm pump with a metallic and non-metallic tube-shaped diaphragms. Here you can see how they push and pull action of a plunger cause expansion and contraction of a diaphragm. Well, this is a video of a prototype diaphragm pumps. For this presentation, Fuji Techno made a transparent pump to show the movement of a plunger and the tube-shaped diaphragm. Unfortunately, I got difficulty to run this video today. So this is the end of my presentation. Thank you very much for your attention, and I hope you found it informative. Thank you.
Thank you very much, Mr. Morikawa. Ladies and gentlemen, this is the time now to ask questions. And you can raise your hand electronically and we'll unmute you so you can ask your question in real time. So to make it as realistic as possible. Alternatively, you're welcome to type the question in the Q&A box or type it into the chat box. I believe Dr. Wiles has a question for Mr. Morikawa. Dr. Wiles, please proceed. Thank you.
Thank you, Harry. As always, I always have questions. Something that people are questioning is kind of preventative maintenance. When you're operating in the lab, that's okay. You can be doing lots of different chemistries. But if you switch over to a continuous plant that might run for 8,000 hours a year, what's your advice on preventative maintenance time periods, and what kind of work would they do for your pumps?
Okay, our pump is just like automobile engine. You need to replace the oil once in a while. And I would say every 3,000 hours of operation, you need to replace oil in the cam box. Also, the plunger seals. It's ultra high molecular polyethylene or PTFE, whichever. But it's depending on the liquid, also pump speed. You are running the pump. We recommend the customer to replace those plunger seals once a year, but depending on the condition of a plunger seal. Other item for replacement is gasket O-rings in the pump head. But most of our customers prefer couplets or couplets. Couplets. So the couplets are very durable, long-lasting material. So most of the customers are using, the pump with the same gasket, covered gasket, like 5 or 6 years without any issues.
Super. So that would fit with kind of scheduling twice a year. You do your oil replacement and you do your seal replacement if you need to. So right. That fits with how we would run our plants as well, with a typical once or twice per year shutdown plan. Thank you very much.
You're welcome.
Right. So, ladies and gentlemen, there's a couple of questions that have come through the Q&A box, which we'll read and then can be addressed. I believe the first question is for Mr. Morikawa, and the question is as follows. The super metering pump, is it capable of handling solutions with solids? If yes, to what extent of solid concentration? Okay,
every particle slurry is different in terms of like a particle size, shape, separability. So it's dependent on slurry. We need to understand the detailed specification of the slurry the customer is talking about. Depending on the specification, we can configure the pump to handle slurry. In particular slurry, we have very high success rate, and we got lots of data experiments in the past. So I would say depending on slurry, but as I said, we got a good success rate. But I'll just explain to the audience my presentation. We are now developing a very unique diaphragm pump because of the high demand for handling a wide variety of slurries. People are very demanding, So we're developing this diaphragm pump. The pump will be displayed, I think, next year. But at this moment, if your customer, customer got some issues with liquid slurries, please get in touch with us and inform us of the detailed information, and more than likely we can come up with a solution.
Thank you. There's another question. I believe it's addressed to Dr. Wiles. Is there any customer case for heterogeneous reactions, Dr. Wiles?
Oh, absolutely. Not with our static reactors. So we're typically looking at liquid-liquid, gas-liquid, immiscible liquids. We have a tolerance for a small amount of solid, but as Mr. Morikawa just said, slurry handling is all dependent on what the slurry is, what the solvent and solid combination is, the settling characteristics. So for a static reactor, it's hard to say that it will be handled. So we prefer to work with a partner that has an actively mixed reactor or a series of CSTRs, so that you can handle the slurry with the best characteristics for maintaining suspension and decouple them from actually the net flow that's needed for the reaction. So as a generic answer, I would say go for an actively mixed reactor. It's not that static can't handle some solids, but it's very specific to the reagent composition. So if you would like a generic high loading palladium on carbon hydrogen, for example, go for an actively mixed flow reactor. But there are plenty of examples in the literature of that.
Thank you. I have a big picture question. So with respect to batch versus flow, what's the prevalence, what's the penetrance, if you will, of flow in the API field or in the pharmaceutical industry? In other words, how much has flow taken market share away from traditional batch-based synthesis?
I don't think it's taken away market share. I think it's added to the capabilities. So what we saw initially, say 20 years ago, people were looking at putting every transformation from batch into flow and just seeing what was possible. But now it's more shaking out in terms of quality, amount of material, and accessibility to chemical transformations. So I think it's accessing techniques that wouldn't necessarily have occurred before. Mm-hmm. So it's complementary, it's not replacing. Right. And we, especially if you look at photochemistry, there was no solution for that. So that space is increasing, but it hasn't necessarily replaced batch. It's added to the capabilities. So I would say in the last 5 years, it's increased dramatically within the major pharmaceutical companies, getting from piloting into manufacturing. But it's more prevalent in specialty and fine chemistry, mm-hmm. where you can go to market quicker. So I think the lead time from discovery to manufacturing, the trajectory is long for an API anyway, and we're looking typically more at the second generation type of processes. So I think we're still in early days. But if you look at the key raw materials and where people are struggling with highly functionalized fluorinated nitrogen containing compounds, you do see penetration there. But I don't personally see it as taking away part of a technology so much as adding to it. But the penetration has definitely started to increase, and the openness companies are willing to say that they're doing it has definitely increased in the last 2 or 3 years.
Thank you. There's another question that has come in from the audience. Let me read it out. And it is, are there any examples of crystallization in flow reactors? Dr. Wiles, would you like to take that, please?
Oh, absolutely. Again, continuous crystallization. There are examples, not necessarily done in static reactors. Again, similar to the slurry handling, you'd look at an actively mixed reactor. So that could be a series of CSTRs or mixed product removal units, or an actively mixed flow reactor again could be used. It's a very different end of the spectrum to what we do, which is the fast, highly energetic. You're going to the more gradual temperature and a slower evolution. So, but there are oscillating baffle reactors out there. So there are plenty of opportunities for the downstream as well.
Right. I believe there's no further questions. Ladies and gentlemen, if you'd like to ask questions, please ask. This is a great opportunity to hear from the leader in the field, Dr. Wiles, who knows this field better than anyone else. We host so many flow chemistry conferences, and whenever Dr. Wiles presents, the last one I remember was in the UK, it was a packed room. So this is before the pandemic. So we hope to get to those days soon enough. But in any case, if you do have questions, ladies and gentlemen, this is a good time to ask. Alternatively, you could reach out to us and we can forward the question to Dr. Wiles as well as to the Fuji Techno team. Finally, we're recording the webinar. So once we get approval from the speakers, if you'd like a copy of the webinar, please reach out to us. We'll get approvals from Dr. Wiles as well as Mr. Morikawa, and then we'll edit and curate the webinar into its components and send it over to you. So we'll give it one more, it's a last call. There is one question that just came into the chat, which is, it's unclear, it's not fully written, so I'll try to paraphrase it. Could you guide me as to dosing or slurry? I'm not sure if I'm correctly addressing it, but do either of our speakers want to address it?
Well, I need detailed information about what's slurry this talking about. We didn't understand. Yes, we can be confident also to handle.
Right.
But to please be more specific about slurry.
Yes, it just came in. So let me read it now, the more detailed version. Could you please suggest a pump which can handle a slurry with solid concentration of 30% with maximal particle size of 150 microns?
Well, we also need some more info about the shape of the slurry and the particles. As I said, one of our pumps are being used by the generic manufacturers to handle the carbon catalyzer 100 micron with percentage 15%. And we got the larger pump which can probably handle the slurry this person talking about, 150 microns. But we need more detailed info. Because separability is very important matter, and the hardness of the slurry.
So another version of the question came in from another attendee who says the solid is present at 36% in the slurry mass and the particle size is 370 microns. Not sure if you can address that, Mr. Morikawa.
Probably this person need the diaphragm pump we're developing now, so please wait until next year, ahead of time.
Okay, right. Any further questions, ladies and gentlemen? This is your last call. If not, we'll like to thank our speakers. We'd like to thank Dr. Wiles for a fantastic presentation. Thank you very much. And we look forward to welcoming you as keynote speaker to SelectBIO flow chemistry conferences worldwide. And we'd also like to thank the Fuji Techno team, Mr. Morikawa and colleagues for sponsoring the webinar and for their presentation. And ladies and gentlemen, we'd like to thank you for your participation. And please reach out to us if you have questions and we'll be forwarding them to the speakers. Thank you, everybody. Goodbye, and hope you have a great day. Thank you.
Bye, everybody. Thank you.
Goodbye. Thank you. Bye. Bye for now.